Okay, so I wanted to go over just a few things about vibrations and waves, just go over some notes, some basic notes. Most of these you will probably already know. First of all, what is a wave? Well, a wave is a rhythmic disturbance that carries energy through matter or space. Of course, we discovered that the velocity of this wave depends on the medium, and this is just the material through which a wave transfers energy. It can be either solid, liquid, gas, or a combination. It can also be electromagnetic waves, which don't need a medium. And this is like radio waves and visible light. So how is a cycle different from a period? Well, a cycle is one full oscillation where the wave begins to repeat itself, whereas a period is the time it takes to complete a full cycle in an oscillating system. So the cycle is the physical amount compared to the period is the time it takes to go through that physical amount. So the simple harmonic motion, or SHM, we've been studying for a little while now, and it's just the back and forth vibratory motion, also called oscillatory motion, of a swinging pendulum, or anything that just repeats itself. So a sine wave, you've seen sine waves, and this is just a pictorial representation of a wave. And this is Frank Oppenheimer down in these pictures, and of course he worked on the Manhattan Project, but he also was one of the founders of the Exploratorium in San Francisco. He's demonstrating waves here. So how would a weight attached to a string behave? Well, a weight attached to a string, or a spring, undergoes simple harmonic motion. You guys have seen this already before whenever we did this. Now imagine you have a marking pen attached to the bob. This would trace a sine wave on a sheet as the sheet moves to, say, the right underneath it, creating this pictorial representation we call a sine wave. So one thing to keep in mind is what is a crest, what is a trough, amplitude, and what that would look like. Say, for instance, what is wavelength? So make sure that you have these in your notes. A crest is just the high points on a wave, and troughs are the low points. Amplitude is where the midpoint, or the point of equilibrium to the crest or the trough. And wavelength is just where it repeats itself. So the wavelength, again, is just the distance from the top of one crest to the top of another one. And it doesn't have to be top to top. It could be trough to trough. It could be where it crosses this midpoint right here to where it crosses it again going the same direction. Frequency, however, is the number of vibrations an object makes in a unit of time, usually 1 second. So frequency is measured in hertz, which is cycles per second. So what does RPM mean? If a car is idling at 600 RPM, what is the frequency of the shaft? So RPM stands for rotations per minute. So a frequency of 1 cycle per second is 1 hertz, 2 cycles per second is 2 hertz, and so on. So 600 cycles per 60 seconds, that's 1 minute, 600 rotations per minute. That would be 600 cycles per 60 minutes would be 10 cycles per second, or 10 hertz. Okay, so how does this play out in our everyday life? Well, let's take AM radio or FM radio, but in this case we're going to look at AM radio. AM radio stands for amplitude modulation, which means that it varies the height of the wave instead of the frequency of the wave compared to FM. FM stands for frequency modulation, and that's going to vary the frequency of the wave just a little bit. So, for instance, if you tune into 960 kilohertz or 960 kHz, this means it's vibrating 960,000 times each second, producing a 960 kilohertz radio wave. So we already know that period and frequency are inversely related. Period is how long it takes to complete one full cycle, whereas frequency just stands for how many cycles it can occur in a given time. So what does waves actually transfer? Energy is actually being transferred in a wave. So think about this. Whenever you see a wave, the wave isn't actually carrying the matter, it's carrying the energy. So if I start shaking this string up and down, you're going to see the string moving up and down, but that back and forth movement is carried throughout the string, transferring that energy. So what different types of waves are there? Well, there's transverse waves. And this just occurs when the motion of the medium is at right angles to the direction in which the wave travels. So this is the one that we saw in the laboratory. And then, of course, there is longitudinal. And a longitudinal wave is whenever the particles oscillate parallel. This is kind of like you're pushing on a spring back and forth, and you'll see pulses of the spring go through. So that's a longitudinal wave. This is like sound waves as well. So does a wave have speed? Well, yeah, we saw this in the lab as well. The speed of the wave depends on the medium. If the wavelength in this situation is 1 meter and 1 wavelength per second passes the pole, then the speed of the wave is 1 meter per second. So I want you to find the velocity of a wave in a wave pool if its wavelength is 3.2 meters and its frequency is 0.6 hertz. Okay, so let's figure this out. First of all, write down what you know. Well, we know that it's asking for velocity, and the wavelength is 3.2 meters, and the frequency is 0.6 hertz. Then we're going to go ahead and work it out. Velocity equals frequency times wavelength. Plug in the numbers, and the answer is 1.2 meters. So an earthquake produces a wave that has a wavelength of 417 meters and travels 5,000 meters per second. What is the frequency? Well, what do we know? Wavelength is 417 meters. Velocity is 5,000 meters per second. It's asking for frequency. Do the work. Frequency equals velocity divided by wavelength. So our answer is 12 hertz. Okay. Thank you.